Hello everyone. In this video, I'm going to talk about two query processing algorithms for the join operation, right? More specifically, we are going to cover nested loop joins and single loop joins. Of course, there are several other algorithms, some which are much more fancy than the basic ones which are going to be covered in this video. Nevertheless, you will get an good idea on how the database systems perform join operations. Okay. Okay, let's get started. So the first one being the nested loop join algorithm. Right. So the from the name of the algorithm itself, you can guess what this is about. Right. So let's say you have two uh, relations, let's say employee table and department table, and then you want to join both these tables on the department number attribute, right? And the simplest algorithm that you can think of, almost in some sense naive algorithm that you can think about, is that you loop over all the tuples of the employee table, and then for each tuple you browse through all the tuples of the department table, right? And then whichever match you return them in the result, right? So this is of course an extremely naive approach, and also inefficient, primarily for the reason is that these, even though the complexity is order n square only, which is what the a typical complexity of a double loop or a nested loop will come out. But when it comes to databases, you have to think slightly better in the terms of the number of disk block accessed, right? So even the naive nested loop join can be optimized for for a better block access, and that is what this pseudocode over here uh, presents, right? So just watch closely. So here, the it does look scary in the sense that I have a nested loop which goes up to 4 levels, right? But rest assured that when we actually go ahead and compute the total cost of this in terms of block access, it actually comes out to be pretty good. Okay, so let's go deeper into how this algorithm is working. Okay, so in the outermost loop, I am going to loop over all the blocks of my relation R. Acha, okay, so one small thing here, so there's a terminology which is followed in the textbook. Let's say that you are joining two relations, relation R and relation S, then it is sort of assumed in the convention that the relation R is the outer relation and S is the inner relation, right? So therefore, whenever we write R join S, we will see that R relation R is on the outer side of these loops. Okay, this is just a terminology. The algorithm works either ways, but just to make sure that we are consistent with the terminology here. Okay, so we have two relations R and S. Let's say R is your employee table and department is your S relation, right? So first what we do is that in the outermost loop, we are going to loop over all the blocks of the relation R. In other words, we are going to loop over all the blocks of relation employee, right? So as you remember that disk block access is always one block at a time, right? So you read one disk block from relation R, that is what it does first, and then you read one disk block from relation S, and then the innermost two loops, for each tuple in the block which you just read, and for each tuple in the block that we just read from S, so this part is actually joining the blocks that you have just fetched from the secondary memory, right? And now this part is nothing but is just a simple plain nested loop. Let's say let's say that relation R has two blocks, and maybe relation S has, let's say, three blocks. Okay, so and let's say that R1 is the first block of relation R and S1 is the first block of relation S, right? So I fetched R1, then I fetched S1, and then in the innermost two loops, what I am doing is that I am looping over all the tuples of just R1, the block that you just brought into the main memory, and then you are joining it with all the tuples in the S1, which is the first block of the relation S, right? So after this part is done, right, I am going to go back and fetch the second block of relation S. So that, let's say that is block S2, right? So S2 comes in, and then again we in these innermost two loops, what you're doing is you're joining all the tuples of R1 with all the tuples of S2, right? So, so you're matching tuples from R1 against tuples from S2, and then whichever match your condition, you just go ahead and retrieve those, or you store it in a temporary space, and then that gets shown to the user at the end of the whole processing, right? Okay, so the way I'm accessing my blocks is that I'm going to first bring in my first block of relation R, which is in the outermost loop, let's call it R1, and then I'm going to join the tuples in my block R1 against all the tuples in my relation S. So in our example, I think I said my relation S has three blocks, S1, S2, S3. So the tuples of R1 first gets joined with all the tuples in my relation S, which is spanning over blocks S1, S2, S3. Then you bring in the second block of the relation R, let's say R2, and then again you join the tuples in R2 against all the tuples in relation S, which span over blocks S1, S2, S3, right? So even if it looks scary in the sense that there is a nesting of up to 4 levels, if you see the total cost of this algorithm in terms of disk block access, that's not bad, right? So let's just break it down, how this expression is coming, right? So I said that you have you keep on reading blocks from relation R, one block at a time. You first read R1, then R2, then let's say if you had more, then you just keep on doing. So once you read in a block of relation R, which is your outer relation, always remember that in these expressions R is the outer relation, right? So that is the sort of the semantics that we are going to follow in these slides, and even your textbook follows the same. Okay, so you brought in first block of relation R, and then you read the entire relation S, right? Now if your relation S contains BS number of blocks, then the number of times your relation S would be read would be once for each block of relation R. So here B subscript R is the number of blocks in your relation R, right? So this whole expression BR times BS signifies the fact that your relation S is going to be read once for every block of relation R. So these many number of read accesses to the secondary memory will be done just for reading the relation S. And then you do have to read relation R also, right? Even though it is just one block at a time, and no block of relation R is read more than once, right? So the total number of block accesses for this block nested loop join would be BR plus BR times BS, right? So where BR is the number of blocks in the outer relation, and you read the outer relation only once, and BS is the number of blocks in the inner relation, and the inner relation gets read once for each block of the outer relation. So therefore the total expression comes out to be BR times BS plus BR. Okay, now a couple of things to remember in this situation here. So one thing is that for this algorithm to execute, you need to have at least three memory buffers, in the sense that you need to have space for storing at least three blocks from your secondary memory at any point in time. And how does that work? So let's say you have buffer locations as mm1, mm2, and mm3, right? So each of these locations, mm1, mm2, and mm3, they can store one disk block in main memory, right? So mm1 is the a memory location in your main memory, and let's say that mm1 can store one full disk block or page, whatever you want to call, right? So it can store that much in its location, right? So I need at least three of them. And how would these three be used? So first I'm going to bring in an disk block from my outer relation R. Okay, and then in the, and let's say now I'll put it in mm1 location, right? And now in the mm2 location, what we are going to do is that I'm going to keep bringing one block from relation S at a time. So first I'll bring S1, then I'll bring S2, and then so on, right? So what, when we have S1 in mm2 location, and then I have R1 in mm1 location, then both of these can be joined using the the nested procedure which I'm showing here, right? So for each tuple tr in br, and then in the inner loop for each tuple ts in bs, you check the join condition and add it to result. So the third block, mm3 location, typically what that would store is, that would store the temporary results, right? So when you're joining r1 with s1, some tuples do get matched, and they will be part of your result. Those results are temporarily stored in your location mm3, and as and when mm3 gets filled up, you write it onto disk, right? And I think many of you may have already guessed this fact, that as you are joining tuples from R1 against tuples from relation against tuples from S1, theoretically speaking, you can have TR times TS number of results from just the first block of relation R and the first block of relation S. Let's say that it is theoretically possible that in the first block of these two relations, all tuples match with every other tuple, right? So then that location, mm3 location, which is storing the temporary results, will get filled up much more quickly, right? So as and when that gets filled up, you keep writing things into the secondary memory, right? So if you ask, if you are, let's say, extremely strict in your cost expression, then what will happen is, so this part of the expression is okay. There's nothing wrong with here. Br times bs plus br, right? But the key thing to note is that this expression is just the cost of reading the relation R and S in your algorithm. There is an extra term called as, typically they call it as, blocks required to write the intermediate results, right? But when you are actually comparing algorithms, if let's say, if this is being seen inside an query optimization engine, right? So it will have different options for your for performing your nested loop join. And then whenever a query comes, it will evaluate the cost expressions for different join algorithms to see which one is the best, right? So when the query engine is evaluating these expressions, uh, there is an extra term called as cost of writing the intermediate result. So in this textbook, and in the in this particular course at least, we will not consider that extra term, which is the cost of writing the intermediate results. Primarily the reason being that it's hard to estimate that, until unless you have in your actual databases, they maintain some histograms and all that, and using those histograms they estimate the cost of the intermediate result. But you know uh, and for a UG level course, it's too much, right? So if a question comes in your exam saying that, this is your query, determine the most efficient way of executing this query, then you have to evaluate expressions to determine, which algorithm has the lowest cost, right? So then use just these expressions where the total cost is counted in the terms of number of blocks accessed from the relation R and S, right? And we ignore the cost of the intermediate results. Okay. Okay, now this part, here I have written something called as, when you have only three disk blocks, this is the cost, right? And even for this, you have to check a fact. You have two relations R and S. They both will have different sizes, okay? And this is the expression when the relation R is on the outer side, right? So now when you have two tables in your query, like let's say employee table and department table. Now, depending on whether you put department table outside or whether you put employee table outside, your total cost will be different, right? So, whenever a problem comes, you have to evaluate even the decision on which block should be decided as the outer block, outer relation. Sorry, I mean, given employee and department, you have to first decide that, okay, if I put employee table outside and then do block nested loop join, what is the cost? Versus if I put department table on the outside, I means, I take R as the department table and then evaluate how much blocks do I transfer, right? So you have to do both of these things, right? One last caveat. So that was ordering of the relations inside and outside. And the second caveat is that, if your main memory size is big enough such that one of the relations between R and S can fit in your main memory completely, then this algorithm changes, right? So, I would like to highlight this fact that, this expression is only when you have three disk blocks in main memory and neither R nor S fit in main memory. Okay, so yeah, so remember this whole expression is running under an assumption that we have only three disk blocks in main memory and neither relation R nor relation S fit in main memory, right? But if it so happens that if one of the tables can fit in the main memory completely, okay, then the expression changes. So when I say fits in the main memory completely, you should take it with a pinch of salt. Let me just update this sentence so that you don't get the wrong picture here. Okay, so the way you have to see is, uh, your one of the relations should fit in the main memory completely, and let's assume that that relation is S, which fits in the main memory completely, and you still have space for one disk block of memory from relation R, or just you have space for one disk block of memory, and you have another one disk block worth of main memory space for storing the intermediate results, right? So under these conditions, S fits completely, and you have space for storing at least one block from relation R, and you have some space for storing the intermediate results also, right? So under these conditions, what you do is that, your block nested loop join sort of changes, in the sense that you don't loop over relation S anymore again and again. What you do is that you just make one pass of your relation S, and then you bring the entire relation S into the main memory, and then you sort of fix one worth one disk block worth of space for reading relation R, and what some space for storing the intermediate join results, right? And then what you are going to do is that the relation S is now completely in the main memory, so you're not going to loop over it one more time. However, what you have to do is that you start bringing the blocks of relation R one at a time. So you first bring R1, and you join with all the tuples in your relation S which are already there in your main memory. Then you bring R2, then again you join with all the tuples of the relation S which are already there in the main memory, right? And you keep doing it. So when you have things like that, your total block accesses will change. So here, when we are doing this, what is happening is that we are reading relation R and relation S only once. Right? So we are reading one block of R at a time, but if you see closely, the blocks of R are never read twice, and blocks of S are also never read twice, because in just one pass you just bring the entire thing into the main memory, right? So in such a case, your total number of disk block accesses will be BR plus BS. Okay, so hope you got an idea on how to evaluate the cost of block nested loop joins, right? So the algorithm looks very straightforward, but depending on how your conditions are, the number of block accessed will be changed. This expression will be changed, right? So the typical question that you can expect from this particular module or this particular topic is that I'll give you a query like this, select star from employee comma department, where employee dot department id equal to department dot dn. Maybe I'll give something like that. So I'll give you a query, and then I'll specify the number of blocks in your employee table, number of blocks in your department table, right? And then I will also specify uh, how much space is available in your main memory in terms of number of disk blocks that can come in, right? And given all these things, I will ask you the following question. I'll ask you to determine the best way of executing this query in the database engine, right? So then what you have to do, you have to check for three things over there. First, you have to check if your main memory, the amount of space in the main memory which I have given you is if one of your relations, either employee table or department table, can it fit completely in the main memory, but leaving space. It's not just that you have 10 blocks in the main memory, and your relation S, which was the smaller one, also was 10 blocks. So it's not like you just store the 10 blocks over there, right? That is incorrect. You have to check if you have enough space in your main memory such that three things come in. One, the entire relation S should come in, and you should have space for one disk block, which you will sort of reserve for relation R. And then you have one more disk block for storing the intermediate results, right? So it's not just that S fits in the main memory completely. You should also have space for these two, otherwise you are going to have an incorrect estimate. Okay, so first you check this, if this case holds. If this case holds, then the total cost of the block nested loop join will be this, and then you have to write that in your answer, that I have enough space to execute this kind of an block nested loop join. I will expect that in the answer, right? But if this is out of question, if you decide that you don't have enough space to pull this off, then you come here. And when you come here, you have to again check two things. As I said, you have two tables, employee table and department table. You have to check the total cost that your algorithm is going to require when employee table is outside or when department table is outside, right? So you have to compare both those costs, and then sort of return the best way of solving this. Okay, so yeah, so it's not a complicated thing. You just have to be careful in not to miss any aspect, right? So I think that would be all for block nested loop join. Okay. uh, Hope you understood these things, and you let me know if you have any trouble. Okay. Okay, let's continue with single loop joins now. So in the single loop join, the basic structure is that there is an outer relation R, and then we loop over the outer relation R, and then for every tuple from the outer relation R, we use an index on the inner relation S to see if there are any tuples which match the outer relation R, right? So the reason this is called as a single loop is that there is only one loop in the whole join algorithm, right? So I think this is just an terminology which the database people started using, and then now they continue to use it, right? So yeah, so just one more time. So in a single loop join algorithm, you have an for loop. With that for loop loops over the relation R, and then for every tuple of the relation R, we use an index on the relation S to bring out any tuples which match your join condition, right? Of course, that there are some hidden assumptions. I should not say hidden, they're pretty obvious, that the first of all, relation S should have an index, and the index should be on the attribute which is which is being considered in the join condition. Otherwise it's no use, right? Okay, so now for this single loop join, let's try to derive some cost expressions and get an idea on how many uh, buffers in the main memory do we need to have this algorithm running in place, right? So first case, let's say that you have a primary index, or for that matter even b plus tree index on the relation S, and the join attribute, or the attribute which is being used in your join condition, happens to be an key attribute of the relation S. Okay. Under this assumption that join attribute is a key, if this is really the case, uh, then what happens is, no matter which tuple you pick from your relation R, right? So no matter what tuple you pick from relation R, that tuple will match only against one tuple from relation S, right? Of course, there is an implicit understanding is that your join condition is an equality condition, something like this. Let's say you have the query select star from employee comma department, where employee dot DNO is equal to department dot department ID, right? And this department relation is your, let's say, would be your relation S, and right, and the department ID is a primary key, or a unique key in your department table, and then the join condition which you are using in this particular query is an equality, right? So under all these cases, now what happens is that every tuple from your outer relation, which is the employee relation, so you're going to loop over the tuples of the employee relation, and any one particular tuple from the employee relation, and when you take out its department number attribute, that will match only with at most one attribute, or at most one tuple from the relation S, right? So under this assumptions, you can have a pretty confident statement like that. Now when you're having only one match from the inner relation, then your total cost of executing this algorithm becomes something like this, right? So over here, the first part, this is the cost of your reading relation R. In our example, this was the employee table, right? So you read one block at a time, and then let's say first you read R1, the first block of relation R. Then from R1 you pick up the first tuple, and then you search in either it was, even if it was a primary index or a B plus tree, doesn't matter. So you search in that tree. So you will require height plus one block accesses. So height is the height of that tree, whether in a primary index or B plus tree, and then one additional block access to actually go and fetch the record, right? But given that we have assumed that your join attribute is a key attribute of relation S and so on, we are sure that for every tuple of the relation R. So mod R is the number of tuples in the relation R. So we are sure that for every tuple of relation R, we will require only these many extra block accesses and nothing more, right? So we are sure of it. So therefore, the total disk accesses will be given by this expression, right? Of course, as I said before, there is also an extra cost of writing the intermediate join results and all that. But in this UG level course, we are sort of ignoring it, right? So if even if you understand this part, you are good enough for CS301. Okay. Okay, I just updated the slide to write all the assumptions which I just covered in the video. Okay. Okay, let's go forward. Okay, let's cover the case of a single loop join when your index on your relation S happens to be constructed on a non-key attribute, right? So as an example, you can take our employee and department table, and we are interested in joining them on the department ID, right? So, but here, since we need to make it as an example of non-key, okay, we'll do the following. So we will make department as the outer relation R. So in this example, for this, make department as the outer relation R, and you're going to loop over all the tuples of the department, and then for every tuple of the department, you're going to search on an B plus tree, which is constructed on the department ID of the employee table, right? So that sort of illustrates this case, right? So now, given that we are using the B plus tree on the department ID of the employee table, it's a non-unique attribute of the employee table, because you will have several employees from the same department, right? So therefore, if you pick any one particular tuple from your outer relation R, which is a department in this case, let's say you pick up computer science department. So the computer science department is going to match with all the computer science department faculty, which is sitting in your employee table, right? So what would be the number of block accesses for that, right? So this part remains the same. Cost is that you have to read the outer relation, which is department in this case. You have to read the outer relation once, and for every tuple of the department relation, we search through the B plus tree, which is on the department ID or department number, whatever you want to call, on that at a column of the employee table, right? So how many block accesses will I have in the B plus tree part? This expression, you may recall it from your earlier video, which covered searching on B plus tree with non-unique attributes, right? So this expression is very similar to that. Let's see how this can be understood here, right? So you are giving a department number, let's say computer science department, and you have to now retrieve all the tuples from the employee table where that department ID or number is computer science, right? So as I said before, whenever we are constructing an B plus tree on a non-unique attribute, the tree by itself will contain only the unique values that appear in the column, and then at the leaf level, for any one particular uh, department ID, I will store a pointer to a disk block or maybe disk blocks which contain the addresses of all the tuples where that particular department ID appears, right? So if my department ID is computer science CSC, right? So I'll search, I'll access height number of blocks in reading the B plus tree from root to leaf. So that height comes here, and then I assume that SB is the expected number of records for any one particular unique value. Let's say if you are considering this departments as the example, then SB, you can expect it to be the number of faculty in a department. I know it's an approximation, but you can store some average value, right? So for any one particular department, you need to retrieve SB number of records from your employee table, right? So now uh, how to get those SP number of addresses, right? So that part is SP divided by BFR of SP. So in the sense that, from the B plus tree, when we are storing those extra blocks of SB number of addresses, that itself will take some space in the secondary memory, and reading those blocks will take this much amount of disk access, right? So this BFRSB is the number of record addresses which will fit in one disk block of your hardware. And given that these many number of record addresses fit in one disk block, now you have to store SB number of addresses. How many disk blocks will you take, right? So this expression ceil of SB divided by BFR of SB gives that number, right? This is the number of disk blocks which are required to store SB number of record addresses, right? So once you retrieve those record addresses, you have to actually go at those record addresses and pull out the entire tuple from the employee table, right? So this SB is for that, right? So the total cost of single loop join when you have a non-key attribute on S and join condition is equality, this is what it is. You loop over the outer relation, and then for every tuple you search on a B plus tree which is sitting on a non-key attribute. So the total number of block accesses just for the algorithm will be this much, right? And as I always say, plus some additional disk block accesses for storing the intermediate results, right? So that part we'll ignore in this course. Okay. One last thing before we wrap up this video is just a brief discussion on how many memory, main memory locations do you need for running the single loop join, right? Okay, so let's start from here. So we're going to loop over R and then search through this B plus tree, right? And then of course you have to store something in your intermediate result, right? So if you want an rough estimate on the number of blocks of main memory that you will need, is that you will store one block where relation R can keep on coming, and you will have one block for storing the intermediate results, which will keep on getting flushed out whenever that is full. So one goes here, one goes for the intermediate, right? And then you will need space for uh, this part, right? Now what you can do is that even if I'm writing height plus 1, right, you actually don't need height plus 1 uh, disk block space in the secondary memory, right? uh, if you store height plus 1, then yes, you will have less number of cache misses. But in the worst case, for this entire thing, even if you just have one block, right, then first the root will come, then the next level child, then next, and so on, right? It will keep on having that, and then finally it will go ahead and pick that record, right? So this whole portion can actually be done in just one disk block. But given that you're going to read this entire B plus tree multiple times through the entire join process, it is advisable to store it is advisable to store at to have more than one disk block for this, right? So because at least if the root can store in the main memory, right, you will have less number of cache misses, but that's mostly on the efficiency part. The same goes here also. So you'll have one disk block sort of reserved for reading the relation R into that, one block at a time. One block in main memory is again going to be stored for storing the intermediate results, sorry, right? So that too is fixed. And then this entire part, right? In the worst case, how many blocks will I need, right? So I should not say worst case, because in the worst case, you can just keep on doing page fault and keep retrieving the records. But if you have enough space to store at least this much amount of disk blocks in main memory from this side, I think you will be okay, right? So basically, one disk block, where you will traverse through the height, and then at the leaf level you just go ahead and read these many number of disk blocks, keep it in the main memory, and then these disk blocks have to be then simply just read to get this part, right? So my suggestion would be one disk block for R, one disk block for intermediate relations, and whatever is this number on an expected scale plus one, wherein where you store this, so then it will be sort of good, right? So the reason I'm telling you all this number of blocks which are required in the main memory is actually database does this estimation internally, right? Even the cache and the main memory in your computer, which is given to the database, it does some efficient things. It allocates the main memory buffers in a way that you get less number of cache misses, or whatever, less number of page faults, right? Because you remember from your operating system that the more the page number for the more the number of page faults, the slower is your performance, right? So the main memory buffer manager in a database, it actually estimates it smartly puts in the buffer so that we can minimize the total number of page faults, right? It will actually go ahead and reserve main memory locations for BR and the intermediate, and then do some smart things in here. It actually does it, right? So there is a very famous algorithm called as dbmin, which is a main memory buffer manager algorithm for database systems. It's actually implemented in real world systems. Okay, so more of that in the advanced database course. But for now, I hope you have understood these cost expressions. Don't mug them up. If you have any doubts, let me know, right? Because in the exam, you can expect one of the following two kinds of questions. So either I give you an algorithm and ask you to come up with an expression like this, or I will give you a general use case kind of okay, let's say this is the query, select star from employee, comma, department, where something, something, and then ask you to come up with the most efficient way of executing that query. And in that case, you have to consider different algorithms and their expressions to decide which one is the most efficient one. And that's how your query optimizer also does it. These expressions are actually stored in your query engine, and for any given query, it estimates the cost of using an algorithm using these expressions only. Okay, so that's all in this video. If you have any doubts, let me know. Thanks.